much for the kind introduction, and I hope that that you can all hear me all right and don't have too many technical problems. I totally get it in these type of remote setups. So I appreciate very much being here and giving you a little bit perspective of our research in the lab and at the university. I have tentatively titled this talk of shapes and spaces because it's about geometry, topology, and machine learning. These are, of course, three big topics, and we won't be covering all of them in the last detail, obviously, but I hope to give you some kind of glimpse into research directions that I consider to be exciting for my lab and for my collaborators. And yeah, let's get started, I would say. So first, just to get some misunderstandings out of the way, let me briefly set the stage. I'm not quite sure whether we have yet, as a community, arrived at a proper definition of AI, ML, and deep learning, right? But my understanding of these subjects is that they're a little bit like these nested dolls, and we have things that are fundamentally about artificial intelligence. So we try to mimic the learning process, maybe of animals or of human beings. Then we have machine learning methods, which are algorithms that somehow learn or adapt to the data at hand. And then, of course, we have the deep learning as one novel direction in machine learning research. Now, this to me means that anything we do in deep learning is also machine learning, of course, right? But maybe not vice versa. So there are some traditional machine learning algorithms, as you could call them, something like support vector machines out there that do not fall under the deep learning moniker. But I don't like to be locked in a small box, essentially. So I like to consider that we are actually doing machine learning research and not just deep learning research. Now, you've heard plenty of things about neural networks as part of these lectures. I saw some of the lectures, and it is amazing to be part of this great lineup. I'm going to give you two slightly different perspectives from what you might have heard, and two maybe slightly easier perspectives or slightly more abstract perspectives. So the first perspective that I like to use when I talk to my mathematician friends is I just say, well, neural networks, you have to treat them as universal function approximators. What does that mean? That means that essentially, under some conditions, we're not going to go into all the details here, under some conditions, you can train a neural network such that it approximates any given function on some nice set that is somehow well behaved, such that the Hausdorff distance to that function is smaller than epsilon. There's multiple versions of these universal function approximation theorems around. I used the formulation by Pincus given already in 1990, and I think it is kind of important to understand that even before the deep learning revolution came in the, let's say, late 2010s or so, there was a lot of research on neural networks as such. This actually dates back to the 1960s. So in some sense, deep learning in theory is not a very new research field. And I'm saying this as an advantage because it means that we can draw upon lots of things that people have tried out. However, this knowledge is also slowly getting forgotten in my experience. So people treat it as if everything before 2010 was irrelevant. That is, of course, not the case. We can draw upon these things from history and see what is going on in the field. Now, that's one perspective, universal function approximation. This means that deep learning is very appealing if you have a complex function that you don't know how to really write down analytically, but you can maybe easily measure it at some point, right? And then you train a neural network to give you an approximation to that function. Very nice. The other perspective, which is also dear to my heart when I wear my computer scientist or my, let's say, more engineering hat, is that neural networks are nothing but smart computational building blocks. So things that fit together like these Lego sets or these blue brick sets or whatever you're using now these days, right? And you can take those bricks from out of a box and you can reconfigure them in different ways, in different architectures, etc. And I think this is also very important to understand because that speaks to the versatility of neural networks as a domain. Previously, when we were talking about classical machine learning techniques, let me just drop the SVM there again. With the support vector machine, you're kind of fixed on one specific model. You learn this maximum margin hyperplane, the separation, etc., and then you're done. With a neural network, you're not really fixed in terms of your architecture, right? When you find that your given architecture doesn't work, you can easily augment it or extend it with different building blocks. So you could say, oh, I'm seeing that I'm somehow not using enough global information. So maybe I add a block that is supposed to be doing that for my data. And this is, I think, a magnificent property to have, and it speaks to us as a community that we can use these properties and build something interesting from it. Now, that's just setting the stage. Now, let me slowly pull us back to math. Where does math come in? Because I used to be a mathematician, maybe I still am, I don't know, I consider myself to be a mathematician and a computer scientist, but back when I studied pure math, and in particular algebraic topology and differential topology, I was always amazed to see how vast math is as a land, or as a continent almost, right? So you have so many different disciplines that are working together, and this is beautifully illustrated in this map, which I kindly obtained permission from Dr. Franka Miriam Brückler for using this. So thank you very much, Professor Brückler, for allowing me to put this in there. This is a really beautiful illustration that shows how the different disciplines are working together. We have the statistical folks, we have the analyticians, we have geometrists, we have topologists, etc. Right? And math is really, really vast and permits different perspectives on different things. And so to me, it was only a matter of time to see more and more mathematical concepts, I guess, or mathematicians going into the field of machine learning, because they found either that it would be interesting to try out some of these things for their own research, so putting it back into math, or actually trying to explain certain phenomena in machine learning research itself. And we're going to see different perspectives around this in this talk. But I'm using this to illustrate that math, just like machine learning, is really vast. It's not everyone who does math understands everything about the field, just like not everyone who does machine learning understands every little detail about machine learning research as such. And I think that's fine. This is normal with big fields and with complicated universes that we're living in. Now, let's zoom in a little bit on this continents. And I'm going to talk about three different things, three different fiefdoms, as you might want to call it, to stick with this math metaphor or with this continental metaphor, namely topology and three of its, well, different fiefdoms or kingdoms. And specifically, I want to talk about point set topology, algebraic topology, and differential topology. Now, please, for those of you who have a mathematical bent, please don't take these definitions too seriously. It's actually very, very hard, just like a border that might shift at any time. It's really, really hard to say sometimes where one land begins and where the other one ends. But I'm trying to give you, let's say, some core questions that these research topics, these research fields are interested in. And for point set topology, the bigger questions are, what does it actually mean to have a continuous function, to have a compact set, or to have connectivity in a general space? We all know these things from the Euclidean space, but as you all know, mathematicians like to think in generalities and in different categories. And if we have one concept that works nicely for the Euclidean numbers, why not, or for the Euclidean vector space and whatnot, why not try to make it work in other spaces as well? So that's what point set topology is all about. It's basically defining and bringing all these concepts into a more generic framework. Now, algebraic topology, one of the fiefdoms that is very, very dear to my heart because I studied it at nauseam almost, is concerned with the question of what are actually characteristic properties of spaces that we can capture using algebra, so using counting, right? Using counting techniques, using linear algebra techniques. By contrast, we have differential topology, and you can already see that there's maybe sometimes kind of a bridge between those two countries. And in fact, there's theorems that bridge those lands as well, and I'm going to name a couple of them later on. But differential topology, by contrast, is concerned with finding the same characteristic properties or different ones, but the ones that can be captured using calculus or using a kind of, let's say, function-based analysis. This will become hopefully clear later on. And again, these are not the best succinct definitions that you could do, but I think it serves well as a starting point for a discussion. Now, let's zoom into algebraic topology a little bit. There's a couple of ways to think about what you would do if you were an algebraic topologist. First of all, you could say very abstractly, yeah, we develop invariants that classify topological spaces up to homeomorphism. You could also say, well, we use tools from algebra to study topological spaces. But the definition that is, I think, most, in a sense, encompassing the spirit of the field is if you think about that algebraic topology aims to understand shapes through calculations. What does that mean? Let me give you three tastes. The first taste, which you might have heard about, is the so-called Seven Bridges of Königsberg. So Königsberg is a city that was reasonably big, and someone wanted to know whether there is a walk through the city that crosses every bridge in this city exactly once. And this is a map of the city, a contemporary map, and then none other than Euler himself was tasked with this idea of figuring this out. And his great insight was that one can actually model this problem not in a geometric fashion where you actually look at the map and you see what paths you could take and it's very complicated, but rather you could abstract that and form a graph. And the graph is built by considering all the land masses and then just connecting different land masses if they are connected by a bridge. So the bridges are the edges. And then his statement famously is that no such walk can exist because there are more than two vertices, more than two land masses with an odd degree, and this doesn't work out because you have to go in by one bridge, go out by another bridge, since you're supposed to use it exactly once. And the lesson here, I mean, this is not a problem that we need to solve now anymore. That's clear, right? But the lesson here is that topology, in particular algebraic topology, helps you abstract away some things from your data and then makes it maybe easier to handle. Now, the second test that I want to throw at you is known as the Euler characteristic, and you can see that Euler is a man to be counted on when it comes to algebraic topology. So he has, of course, many more distinct advances and improvements in mathematics, but in topology, he's really a household name. Now, the Euler characteristic is a count statistic defined for a polyhedron. And it's defined as the number of vertices minus the number of edges plus the number of faces, so V minus E plus F. There's other definitions of the Euler characteristic that have been generalized to simplicial complexes if you're into that, or to combinatorial complexes, of course. But for now, let's just stick with that. Why is that interesting? Well, if you take a polyhedron, like a Platonic solid, then you can actually calculate this quite easily because it's just V minus E plus F, right? It's a very simple algebraic formula. And then you find that actually the Euler characteristic chi of all of these polyhedrons, all of these Platonic solids, is 2. And in fact, interestingly, it's actually sometimes used as a definition for a Platonic solid, but let's not get into that. But that's a deep fact that you can actually use that to detect whether something is or is not a Platonic solid, right? Or whether it is whether it's homotopy equivalent to certain things. So by the way, I'm using some terminology here for those of you who are already familiar with it, but if you're not, then this is also good. I think that the take-home message should just be that even such a simple count statistic can serve as a way to characterize a shape to some extent. Of course, it's not infinitely powerful, but it serves as a good starting point. Now, the third taste that I want to give you are the so-called Betti numbers, and these are somehow intricately related to the Euler characteristic. In fact, you can show that a alternative definition of the Euler characteristic would be the alternating sum of the Betti numbers. But nevertheless, you can also define them in different ways. And the idea, without going too much into the details, how they're being calculated is that you take it to represent the number of d-dimensional holes in the data. And you can use that to distinguish between spaces. There's even a very nice, let's say, conceptual, intuitive definition of what these Betti numbers mean. For d equals 0, these are connected components. For d equals 1, these are cycles. And for d equals 2, these are voids. And now what we can do with this is we can start tabulating spaces. So we can start with a point. A point is very simple. It just has a single connected component, nothing else. So its signature is 1, 0, 0. A cube is a little bit more complicated. It has one connected component and definitely one void because it's empty, right? It's a cube. So we get a signature of 1, 0, 1. And we can play this game again. The sphere is similar. It also encloses a void. And now we get to the torus, which suddenly we find has two cycles. I sometimes show this torus then highlighted with these cycles, but for here, let me just tell you that one of the cycles is the one you would expect, namely the one in the middle, and the other one is the one that you would use if you were to hang this torus into a tree, right? You would take a piece of thread and you would tie it around the torus, and then you would hang it into a tree. The bottom line of this is that even though these objects look quite different and they can be quite complicated, in particular if you think about now different objects that are embedded in some very high dimensional space, these simple count statistics, again, these simple Betti numbers help you gain a signature of the data, as it were, to distinguish between them. So you can say, well, a torus is definitely not a sphere. And this sounds trivial to us now when we discuss this in terms of shapes, but it's absolutely not a trivial thing to do when you're not knowing all the characteristic properties of a data set in a high dimensional space. So being able to tell those two spaces apart is already a very, very good feat of this simple count statistics. But we also know that reality is rather messy, right? We're not dealing with Platonic solids. We're not even dealing with the Platonic ideals of these objects, but rather we are dealing often with just data, right? Data that is sampled from some object, data that has some kind of generative process underlying it, and we want to still be able to capture its properties. And this is where the illusion or where the intuition that I gave you, where that somehow breaks down. Because to a topologist, if you're like a pure topologist, you would say that this thing on the left-hand side, this blue set of dots, this has no topology, or rather it has the topology of every individual dot is its own connected component and nothing else happens here, right? This is a very puristic view and a very reductionist view of the data. However, as human beings, we would probably say, wait, this is a torus, or at least it's something that has potentially been sampled from a torus, right? And a lot of time and effort were now spent in, let's say, the last, almost 100 years or so, I guess, to go from this left-hand side to this right-hand side in a fashion that is non-trivial and in a fashion that is well-defined. And to do that, we need to represent the spaces, we need to represent the data that we are dealing with. And one very powerful tool to do so is to use a triangulation. So triangulation is, if you're familiar with mesh processing, is nothing but that, right? You just take triangles and you take edges and you take vertices, and presto, you have a very nice mesh that is triangulated by your triangles. It sounds very tautological when you say it like this, right? However, it's important to notice that triangulations also work in higher dimensional spaces. You just replace the triangles by higher order equivalents, so for instance tetrahedra, right, or something bigger than that. And moreover, the really big upshot of this representation of data is that there are some well-known theorems out there dating back to the 1930s and 1940s that tell us that every smooth manifold can be triangulated. So this means that if we're dealing with a data set that has been sampled from some sufficiently nice process, from some sufficiently nice object, then we know that we can get such a triangulation. And then we know that we thus can use that as some kind of representation. These are very deep results that go back to Cairns or Whitehead. I do have to say that personally, and I'm very happy to go on the record with this, I find the Whitehead paper a little bit more accessible, but still it's very hard to read that unless you have a very strong background in the history of algebraic topology. We nowadays have somehow better ways of representing these theorems. So there's nicer formulations of the proofs of this fact. But nevertheless, it stands. It gives us a way to deal with our data. And why are we doing this? Well, we're doing this because if we have such a triangulation, we can actually put a computer to work at it, and we can let the computer measure certain properties. In particular, we can let the computer count its holes or its topological features, as it were. So we can say, hey, how many cycles are there? how many connected components are there, and how many voids are there, for instance. And this brings us now to one of my favorite techniques. It won't be the only one that we will discuss here, but I would be remiss if I would not talk a little bit about persistent homology. And the way I like to call this poetically is that you use persistent homology as a way to get multi-scale topological features, in that you let the points of your data cross the scales like the clouds cross the sky. So you look at your point cloud at different scales, you triangulate it all the time, and during these triangulations you observe how topological features appear and disappear. Let me briefly walk you through that. That's one of my favorite examples. So we start with this point cloud here, which has maybe some kind of rough shape, although I'm not sure whether I would recognize anything in there, but we can now start with growing some epsilon balls around every vertex, and we can connect vertices if these balls are intersecting. And if 3 balls are intersecting, or if we have a pairwise intersection between all of them, then we would create a triangle. If we have a quadruple intersection, we would add a tetrahedron, and so on. So in the beginning, we can see that not a lot happens. Some points get connected, but that's all. If we increase the radius a little bit, we have more connections here, right? And if we increase it further, we get our first triangles. This is great. And in red, I hope you can see it, we also get our first topological feature, or let's say our first non-trivial topological feature. So going from this scale to this scale, we see that suddenly we have our first cycle that goes around the data. And the beauty of this construction is that we don't stop there. We don't say, oh, we have found a cycle, we're done. But rather, we continue this approximation process, and we find that the cycle still persists. So you can see with my mouse cursor, you can see that it becomes a little bit smaller, but it still is there. And once we increase the scale even further, you can see that it has disappeared. And the big takeaway message and the big insight of persistent homology is that none of these scales are better or worse than other scales, but rather when you deal with point cloud data, you need to look at all these scales and you need to observe the changes in topological features and moreover how long they persist. This is where the method gets its name, persistent homology. There is in algebraic topology, you already have things like simplicial homology and singular homology and stuff like this, but this is for a given triangulation, for a given manifold representation, if you will. Whereas with persistent homology, you start with a point cloud, which on its own doesn't have any interesting topology, but you now watch what type of topologies you observe as you change these scales. And this is a relatively old idea. In fact, it goes even back much more than that. But one formalization that was given in 2002 by Edelsbrunner, Letcher, and Zomorodian, by the way, I think of those, at least 2 of them are still active in the field. So Herbert Edelsbrunner, the first author, is very much active at IST Austria, and I urge you to check out his research as well. So in their paper, Topological Persistence and Simplification, they described persistent homology like this. They said, we formalize a notion of topological simplification within the framework of a filtration, which is the history of a growing complex. So, side note here, this is exactly what we did when we started with the points and we started connecting them. We then classify a topological change that happens during growth as either a feature or noise, depending on its lifetime or persistence within the filtration. We give fast algorithms for computing persistence and experimental evidence for their speed and utility. So this to me is the paper that at least kicked off my journey into the field. I didn't read it in 2002. I read it much, much later, but this was the first paper that I found and that gave me an understanding of the beauty of this method. Because indeed, by this approximation method, you now have a way to assign to a topological feature a lifetime or a scale, a set of scales at which it lives. And this gives you a data-driven way to decide which features might be important and which features might be less important. And I think this is a really strong idea that we still should take into account when it comes to machine learning. For those of you who are wondering at the moment, when is he going to talk about machine learning? We are getting there. I just want to set the stage a little bit with some interesting approaches. Now, I should also point out, because this is really important for the scholarship that we're doing as research scientists, that there's other formulations that occurred even earlier. And none of these formulations are better or worse than the others. It's mostly like they have a different target audience in mind, and some of them, depending on your background, might be harder to access. But I do want to point this out, that research doesn't happen in a vacuum, and so there are people that research similar things, but they don't give it a similar name, and so you might end up with some, let's say, concurrent evolution of ideas. And indeed, Victor Hugo said this very nicely when he said you can't resist the invasion of ideas. So you can resist an invasion of an army, but you can't resist an an invasion of ideas. So if an idea has come and it's time, then you will see suddenly more and more research about it, which coincidentally is also a very good metaphor for the emergence of deep learning techniques. Famously, people like Jürgen Schmidhuber said that they had done a lot of groundwork and a lot of scaffolding in the 1980s already for some of the things that we're seeing just now. And I think this is absolutely true from that viewpoint. However, you can also see that sometimes convergent evolution happens, and you will see that that ideas get rediscovered independently and reframed in a different complex. And so 3 papers to point out here for persistent homology, in case you're interested in those, are by Patrizio Frassini on a distance for similarity classes of submanifolds of a Euclidean space. You can already see by the titles, by the way, that these had different applications or different utilities in mind. Then there's a paper by Sergei Barannikov on the framed Morse complex and its invariance, which describes things like a persistence diagram and a persistence barcode. These are topological descriptors with which we're going to deal in a couple of slides. And then there's a paper by Cagliari and colleagues on size functions from a categorical viewpoint. And all of those have different ways of looking at the same problem, namely, you have data, you have different scales, and you wonder what is actually going on, what features, what types of characteristic properties do I need to look at. All right, now let me finally build the bridge to machine learning land. After this has been out, I mean 2002, right? You can imagine that people started to think about how to use that for machine learning applications. And here I now mean machine learning in the sense of classical machine learning. We'll get to deep learning in a second. So you start with a point cloud, you do this persistent homology approach, which I always reckon is similar to a grinder, to a coffee grinder or something like this, because it grinds down the data into a manageable part. You then calculate topological descriptors. Here I call them persistence diagrams. Their exact shape and form doesn't really matter here. It's just that, think of it as like a feature extraction process, right? And then you throw it in your machine learning algorithm, and then you're done. You do the classification task, and that's it. But that's not all, of course. In fact, this pipeline is, in some sense, heretical, if you want, for someone who's doing deep learning. Because deep learning, when it started out, I would say arguably its first real big success was this ImageNet classification challenge. And this really showed that a deep learning method, a deep neural network, in this case, I think, of course, a convolutional neural network, was capable of outperforming all these, let's say, handcrafted, nicer features from computer vision. And this taught us a very, very deep lesson, namely that sometimes it can be easier to let the data speak for itself and derive some kind of features from the data, rather than us going there and saying, okay, no, we need to pick this feature, we need to pick that feature, etc. So in some sense, this pipeline going just from the left to the right would be easily dismissible by many machine learners, many deep learning researchers as well. It's just another feature extraction method. But it doesn't stop there, because interestingly, there's a crucial insight that also happened like organically around the same time by different people, including my own group back at the time. The crucial insight is that it's actually possible to backpropagate information through this pipeline, meaning that the thing you want to have when you train your neural network, right? You want to have a gradient. And this gradient actually exists under certain mild conditions. the conditions are really mild in practice. It basically just means that you shouldn't have points that are too close to each other, or that have the same coordinates and these sort of things. So these are really mild conditions which you can easily achieve and conserve in practice. And indeed, there's interestingly three different papers from three different perspectives that show you how to work with this. There is a paper by Mathieu Carrière and colleagues on optimizing persistent homology-based functions from 2021. If you only read one of those, I would say please read this one because it is great. Then we had our own paper on this called topological autoencoders, in which we show that we can obtain a differentiable loss term for neural network regularization. And finally, we have Poulenard and colleagues on topological function optimization for continuous shape matching. So you can see that they target different things. But the takeaway message is that persistent homology is not just a static pipeline, but you can also use it in dynamic fashion. Now, some success stories of this pipeline, because I think we, in math, and here I'm wearing a little bit my math hat again. In math, we don't talk about success stories too often. And I think that's a problem. We always believe that the world will already find out about our research, which I still believe is true, but it just might take a little bit longer. And I think for persistent homology and for some of these methods that have that are developed in its vicinity, we are really not good at pointing out what these things can already do. And so here are some papers, and since you will have the slides available, you can also find the links later on. First of all, there's, for instance, a topological attention paper which improves time series forecasting. Very interesting work by my colleagues Sebastian Zhang and friends. Then we have our own topological autoencoders paper, which helps you gain faithful low-dimensional representations. By faithful, I mean topologically faithful, so they represent topological structures as much as they can, of course, because when you go from high dimensions to low dimensions, you lose some information. Then we have a particular favorite of mine on topological graph neural networks that actually outperform other methods in structure-based graph classification tasks. So whenever topology is relevant for the graph classification, it really helps, and we outperform everything else. We also have a very interesting paper on topological regularization techniques. One is by our group, Dominic Weibel and friends, where we show that a regularization procedure that includes topology actually helps in 3D shape reconstruction. And the second one is a very interesting, very good work by Hu and friends on topological regularization for improving segmentation results. That's really exciting work, and I do urge you to take a look at this. So these are just some success stories of the past couple of years. But of course it continues, right? There's more than just this type of research. Some of these methods that I presented are called TDA methods, topological data analysis, because they start with the data and they extract some kind of features there, right? But we can do actually more. So I think I'm seeing a question in the chat.
Yeah, sir, I have a question. Yes. Can you go 2 slides back?
Yes.
Sir, in this pipeline, I understand till in the visualization that you've presented, there is persistence diagram, which is basically in a way like summary of the topological features of the point cloud, right? How does that go into the machine learning model?
Very good question. So I wasn't really giving you sufficient details here, but one thing that you can do, you can take a persistence diagram and you can use a vectorization technique. So that takes this diagram, which is essentially a set, and it just applies, let's say, either some convolutional filter to it, or it applies some discretization structure to it, and then you get a very nice feature vector that you can put in. You can also do it in a different fashion if you use, for instance, a kernel method. So we could use a kernel SVM or kernel PCA. Then you can actually take a kernel between persistence diagrams and use the similarity or dissimilarity between them to derive some features. But with neural networks, you even have some nicer methods to put them in there now. You have some kind of learnable projection functions, for instance, that go through this persistence diagram and learn how to project it in different fashions, and then you can use it directly as fixed size as fixed size input data to a machine learning algorithm.
So my question is rather around like what is this machine learning model trying to classify? So we've
Mhm,
reduced the point cloud entire data into this
mhm,
persistence diagram. So we have lost like all concepts of labels like which is one, which is zero. We've lost all that. We just have this persistence diagram which speaks to the the general shape of this point cloud in
mhm,
some n-dimensional space. Now, like what is the machine learning model trying to do on top of you know
mhm.
like
Yeah.
I'm trying to not able to connect that.
Yeah, so classical thing that you do is like you put multiple point clouds in there and then you ask yourself what the label of the full point cloud is. But you are right in that if you want to preserve labels of individual points in the point cloud, then you have to do other strategies. So this is more like a pipeline that tells you something about your global data set or a global instance of the data set, with instance being now a point cloud, some sample, right, some tabular data, stuff like this, or a graph. Um, and we're not answering questions on the local level yet. So we're not doing node classification yet. But I'm going to show you an example of node classification, of local classification later on. And the pipeline can be adjusted. The point of this slide was more to outline the fact that it's not just going in one direction, but actually you can backpropagate. So you can flip the arrows around and you can pull some information from the machine learning task, from the machine learning algorithm, back into the persistent homology calculation.
Okay, sir. Thank you.
Yeah, you're welcome. All right. If there are no other questions, then I would move on to the next field. Indeed, because I want to show that there's more than just this type of approach. And here's my brief attempt at a categorization of things that I found now in the wild. So there's TDA, TML, and TDL. It's very, very hard to keep track of everything. But my humble suggestion is that we use TDA, topological data analysis, to apply whenever you want to describe data using geometrical topological features, which, as a side note here, there is some kind of misnomenclature going on. So even though it's called TDA, so topological data analysis, this doesn't mean that it just captures topological features. There is some interesting research by some of my colleagues that shows that a TDA method, a persistence diagram, for instance, a descriptor, can also capture geometry to some extent. Now, this is a little bit contrasted. So TDA is contrasted by topological machine learning itself, so TML, where I would say use any variant of topology in or for machine learning algorithms, whatever those might be. So if you have an SVM and you use a persistence diagram, then I think you're doing TML, in my opinion. Now, by contrast, you can also say you can use TDL, and TDL would be topological deep learning. Now we're in interesting territory. And here I would say this is when you use any variant of topology in or for deep learning algorithms. And why am I pitching this to you here? I think there's an advantage or certain advantages of this categorization, namely that in this categorization, TDL, so topological deep learning, is actually a subfield of topological machine learning, just like deep learning is a subfield of machine learning. But TML, so topological machine learning in this formulation, comprises actually more approaches, in particular also the use of topological techniques as, let's say, handcrafted features for a machine learning algorithm. And I think we have a second question in the chat about this. Yes, please.
No, there is no question. So
Oh, I'm sorry.
basically,
Okay.
I am addressing the participants that don't ask in between, just ask in the chat. After the session, you can ask and unmute yourself.
Okay,
And
okay. Well, that works for me as well. I just
you
didn't
can
want to
continue.
open the,
You
yeah,
can
I
continue.
just didn't want to open the chat because I'm a little bit afraid that then the rest of Zoom will do something weird. So I rather keep it as it is. But okay, that's very good. Okay, so these are the advantages. So I would say that TDL is a subfield of TML, and TDA as such is maybe a little bit out there in that TDA has intersections with machine learning, of course, but it's not just about machine learning. It does so much more. It has roots in computational geometry, even if you want that. Now, some examples of what one would consider in my categorization as topological machine learning or topology and machine learning. There is Great work by Peter Bubenik dating back to 2015 on statistical topological data analysis using persistence landscapes, which also occurred in the Journal of Machine Learning Research. So you can see that there is kind of a fit in that terminology. There's also great work by my colleague Henry Adams and his colleagues. There's lots of those that I recognize on this paper, but I don't want to read out all of them, on persistence images, which is a stable vector representation of persistent homology. That's also in the Journal of Machine Learning Research from 2017. And finally, that's not the only 3 papers, of course, they're just 3 interesting examples. There's great work by Eric Ameskita and friends on the shape of things to come, topological data analysis and biology from molecules to organisms. And all of these, I would say, under my categorization, are somehow topological machine learning methods because they use topology to address some kind of machine learning task. But we can go further. We can now take a look at topological deep learning. So what is that actually, and where did this term arise? Again, in the interest of scholarship, I did a little bit of a deep dive in history, and I was looking at when did I actually first find this term in a published paper. And there is one paper from 2017 that sticks out. It's by Sichuan Kang and Guo Wei. And they, in my research opinion, coined the term topological deep learning for the first time in a published work. The work is called TopologyNet, Topology-Based Deep Convolutional and Multitask Neural Networks for Biomolecular Property Predictions. It's from PLOS Computational Biology 2017. And the goal of this work was to show how you can enrich a deep learning neural network with topological features. And I think this hits the nail on the head, as they say, because that is what topological deep learning is all about. It's all about improving deep learning research with a more topology-based perspective. There's also an interesting follow-up work from 2021, although I have a slight caveat there. So Effie Love and others propose topological deep learning with a focus on convolutional neural networks. At the same time, there was also a very influential talk by Gunnar Karlsson, here the last author. Now, I'm mentioning this as 2021 because it appeared there on the archive for the first time when I read it, but you can now check out the archive link and you can see that in 2023, finally, they managed to publish this, albeit under a different name. I think it's now published in the Journal of Machine Learning Research, but we can check out those references later. And then in 2024, there was a paper by Papamarcu et al. Outlining the future of these topological deep learning approaches, with the idea that topological deep learning could be the new frontier for general relational learning. And this is the paper that I want to zoom into briefly, because what we said in this paper, I'm a co-author for full disclosure here, we outlined some research directions for TDL research. And we said, in the early stages, the term TDL was often used to refer to the incorporation of features generated by persistent homology within the input pipeline of a deep neural network. However, this paper uses the term TDL to refer to the collection of ideas and methods related to the use of topological concepts in deep learning. So in some sense, it is supposed to be more general, right? And indeed, we find the 3 fiefdoms, the 3 research directions that I showed you earlier, we find those again in the applications of TDL research. We find point set topology again, where the idea is that we extend existing deep learning paradigms to topological spaces. So we look at neighborhoods. We find algebraic topology again, where the idea is that we can improve deep learning models by incorporating novel geometrical or topological inductive biases. So we make the model aware of more things in the data. And we finally find even differential topology there, in that we study topological spaces from a function space perspective. So for those of you who've heard about these terms, the difference between the algebraic and the differential perspective is a little bit like the difference between homology and cohomology. Fundamentally, the goal is the same, but we use it in different ways to arrive at this. Let me make this clear. So one very influential example of essentially point set topology is this paper by Bodnar and others on Weisweiler and Lehmann Go topological message passing simplicial networks. And this is a great example of how to incorporate and generalize this notion of neighborhood from graphs into simplicial complexes in this case. So you can see that, for example, here vertex 2 and this edge in green V5 to V7, that there are different neighborhoods or different types of message passing strategies that can operate on them. So for instance, V2 gets its information from all the connected vertices, for instance, right? But V5 can even leverage something else, right? It can leverage edge information here, but it can also add some kind of vertex-based information as well. That's a great example of point set topology. But there's also more. There's also people that used some kind of operator view on the on a neural network, and there are many papers that I could point out here. In particular, check out the research by one of our co-authors on the TDL paper, Mustafa Hajish, who has very interesting, very good work on CW complexes, for instance. But here I picked this one because I found the illustration very, very exciting for this type of audience. It's by Stefania Ebli, Michel Defera and Gart Breman on simplicial neural networks. It appeared in a workshop that I had the pleasure of co-organizing, topological data analysis and beyond, a workshop in NeurIPS 2020. And the idea is that they use an extension of a Laplacian operator on the graph to make convolutions work on simplices as well. And this basically leverages this whole structure that you have on a convolutional neural network, and now you put it into place for a simplicial complex. I think this is really exciting because it opens up the door towards new applications. Finally, there's also some work on let's say more the algebraic topology route, where we use a topological inductive bias to improve existing architectures. This is with Max, Edward, Michael, Eve, and Karsten, topological graph neural networks appearing in the International Conference on Learning Representations, where, without going too much into the details, this is really a plug-and-play layer or plug-and-play architecture, similar to what I showed you in the very beginning with these Lego blocks, with these building blocks. Here we have a layer that uses differentiable filtrations to make a graph neural network topology aware. And the beauty of this is that this works without changing the dimensionality of your node attribute. So you can literally plug it in the middle of your data set and then you're done, and it will just improve the expressivity of the neural network. We even have something recently going on about smooth features, smooth perspective of features in TDL. So this is, I think, a very interesting work because it completely goes beyond message passing, and it just shows you what happens if you integrate small so-called K-forms, small differential forms on the data. It's therefore also entitled Simplicial Representation Learning with Neural K-forms. It's from the International Conference on Learning Representations in 2024. And I know that we don't have time enough to go into all the details here, but I want to give you a brief glimpse about what this paper is doing. And the main idea is that we use the DRAM map to go from smooth cochains to singular cochains, and then we restrict it using the restriction map to simplicial cochains, which can actually work. So we start with K-forms on the n-dimensional vector space, and we then turn them into simplicial cochains, so into functions that assign a number to a simplex in the data set. And we do this by essentially replacing the evaluation of feature cochains by the integration of differential feature forms. So we use the idea that these type of maps are kind of replaceable in a certain sense, and instead of evaluating features, we just integrate out our differential feature form. The upshot of this is that this gives you a global and local view of the data directly, and there's no need to do any message passing. So it is really a completely new architecture, which interestingly, at its heart, only consists of multi-layer perceptrons. So these differential forms are really just very complicated, nicely built deep neural networks, but they don't have to use any form of like local message passing on the data, which makes them much more robust towards perturbations, and which also coincidentally results in much smaller models, which is great because then you don't have a big parameter budget and you actually train faster and get the same results. All right, with this I have you given a really big tour de force on topology, but you may
Sir,
now rightfully,
sir,
yes.
one question. So the last paper that you showed, simplicial representation learning. So whether it can be applicable for simplicial manifolds or
Yes. This works directly if you have a geometric simplicial complex or an embedded simplicial complex. So you need coordinates at the vertices. It needs to be nicely embedded, but otherwise it works nicely. So we have tried it out for simple meshes already and for graphs. So I think it's a really nice general way of learning, and if people are interested, I would really invite them to check out our implementation, and I think it should be possible to apply this in different for different venues as well.
oh, oh,
But yeah, but with this, I want to briefly move into geometry because this is the thing that I excluded so far, but I started my talk with it, right? I said geometry, topology, and machine learning. So where's geometry in all this? Now, first of all, I think that geometry and topology are not really in competition with each other, but rather they are somehow dual to each other. So I think geometry captures the fine details and gives you quantitative answers, whereas topology captures some more fundamental properties and gives you qualitative answers. And to paraphrase Gunnar Carlsson, I also believe that data has shape, shape has meaning, and meaning begets understanding, but we need geometry and topology in tandem to capture it. Now, underlying this whole persistent homology approach that I showed you, and also underlying, of course, the neural K-forms paper, I think that's a very interesting paper because it actually combines geometry and topology, but nevertheless, we kind of assigned it, at least in our minds, we assigned it more to topological deep learning rather than to something else because the topology part is more apparent than the geometry part. But now let's briefly talk about some aspects of geometry that are more clear in terms of what they capture and how to use them in practice. And to this, I don't want to lose too much time on defining things, but I want to give you a brief motivation about one concept that I think is perfect for showing this duality between geometry and topology, namely that's curvature. You all might have heard about curvature, right? The somehow tautological definition of curvature is that it should characterize how curved an object is, so a surface, a manifold, a topological space. Curvature can be extrinsic or intrinsic. There are some nice properties, maybe Gaussian curvature, for instance, is known to be an intrinsic property of a surface, which is great because it means that it does not depend on any specific embedding, on any specific coordinatization of your data. And you can all maybe remember those type of plots from some lectures. So negative curvature is characterized by this paraboloid shape, and zero curvature or flat curvature is characterized by having a flat plane, and positive curvature is characterized by having a sphere in there, right? Now, here I'm going to speed a little bit up also in the interest of time. One interesting bridge between this smooth curvature for smooth manifolds and the discretized curvature for finite metric spaces, for instance, is given by the Olivier-Ricci curvature formulation. The Olivier-Ricci curvature is often defined on a graph with the idea that you measure how well dispersed the probability mass is when as you move along your graph. So you measure the actual distance of two nodes, and then you measure how a probability mass would be dispersed between them if you have probability measures on the vertices. That is a wonderful piece of work introduced by Olivier in 2009. I can only recommend reading the paper Ricci Curvature of Markov Chains on Metric Spaces. Now, you typically pick this probability measure based on lazy random walks. The exact definition doesn't matter, but the point is that you just say, okay, if I were to walk around my graph in some lazy fashion, or if I were to always use the shortest path distance in the graph, what are the differences that I would observe in terms of the distance or between nodes? And the interesting thing is that you have different regimes in there. You have a negative regime, which is characterized by having more like a tree-like shape. You have a zero curvature regime, which is characterized by a grid, and you have a positive curvature regime, which is characterized by some kind of more clique structure. Unfortunately, the reference doesn't work. I will fix this later, but it's a wonderful paper by Devriand and colleagues. Now, main examples for this are, you can assign this to a graph, you have some kind of slider where you can adjust the laziness of your parameter, and you can actually see that depending on the choice of alpha of the laziness parameter, you end up highlighting different structural aspects of the graph. Now, this is like a little bit of a quick tour de force. There are some useful properties of curvature which kind of connect it to topology again or to geometry. So curvature characterizes graphs in the sense that you know the diameter of a graph based on measuring its curvature. That's really nice to know. Fundamentally, you also know that you don't have to know the curvature values for all pairs, but rather if you have them for all pairs, then you also know, for each edges, if you only have them for the edges, then you also can gain lower bounds for the pairs of vertices for the things that are not being connected in the graph. So it's kind of a neat concept that builds you a bridge between those two worlds. We have leveraged this in practice, or I should say in theory actually, by looking at how well we can distinguish different let's say different types of graphs that are really known to be hard to distinguish, and we can distinguish them using a simple curvature based measure based on the Olivier-Ricci curvature quite easily, and in contrast to a Weisfeller-Lehmann calculation, we are on a par, I would say, or sometimes even better. Not in all categories, but I think it demonstrates that if we had learnable probability measures, so if we would go the final step and we would actually say, well, we learned the probability measure in a task-driven fashion, then we would probably actually also be able to outperform this. So if some of you are interested in this, I would be very happy to hear more about that at some point, because I think it is an interesting research direction. We have just kind of started it. So far, we have leveraged this in practice as well, though. We have two interesting papers out there on curvature. We have one that uses curvature to evaluate graph generative models. That's a Europe's paper from 2023. And we have another paper from 2021. It's a KDD paper on curvature as an efficient graph descriptor for graph learning tasks. So do check those out if you are so inclined. And now, I would get back to the regular programming in a way, and I would talk a little bit more about TDL, topological deep learning, and some recent challenges and some recent research directions that I find interesting. And then we can wrap it up, and I would be happy to take questions. So one challenge in topological deep learning is aptly named the topological blind spot. It's a paper by Aitan and others to appear now in the International Conference on Learning Representations. The idea here is that Aitan and colleagues want to understand and extend topological deep learning through the lens of expressivity. And they stumbled over something that I also consider to be a big problem, namely a lot of TDL methods focus on generalizing message passing to other domains, to simplicial domains, etc. But Aitan and others actually show that this leads to problems, namely, to cite their paper, we then use this criterion to prove higher order message passing, so HOMS, inability to differentiate between complexes based on several fundamental topological and metric invariants, including diameter, orientability, planarity, and homology groups. These limitations are particularly noteworthy as TDL's main goal is to leverage topological structure in data. So to let that sink in for a second, this actually shows that many methods that use the moniker, use the nomenclature of topological deep learning actually are incapable of leveraging topological structures in the data as such. So they are in a way not named correctly. And the lesson here is that TDL is not equal to higher order message passing. This, I think, is a mistake that some folks make. And rather, I would say that TDL is a proper superset, or higher order message passing is a proper subset of TDL. So yes, higher order message passing falls under the nomenclature, under the moniker of TDL. Higher order message passing is fundamentally about topological deep learning, but it's not all there is. So I want to make this clear as like a way to build better nomenclature. And I think there's a big implication for our own research here and for our own models. So I believe that instead of referring to models that use higher order message passing as topological neural networks, we should rather refer to these higher order message passing models as combinatorial complex neural networks. Because combinatorial complex neural network to me would imply that those are neural networks that deal with combinatorial complexes. Similar to how a graph neural network deals with a graph as its input data, a combinatorial complex neural network deals with a combinatorial complex as its input data, right? The combinatorial complex can be a simplicial complex, it can be a CW complex, it can be something else. However, if you call those networks topological neural networks, then to me this would imply that they actually leverage some kind of topological structure of the data. Because in a simplicial complex, you have topological structures that you can capture. You have these ideas that my colleagues Aitan and others showed. You have this idea of diameter, you have this idea of homology groups, etc. Right? And if you call it that, I would expect that you can also capture those properties, but as they showed, you can't. And this brings us to our answer to this type of problem. We believe, and this is something that we also mentioned in our position paper, we believe that one way forward involves new data sets. We need better data sets that actually show the use of higher order features, the use of simplicial complexes, for instance. And this is now current work also to appear in the International Conference on Learning Representations. This is joint work with Ruben, Ernst, Daniel, Mathieu, Sergio, and Carles. We call it MANTRA, the Manifold Triangulations Assemblage, kind of like an assemblage of a nice wine that consists of different things, right? And I'm going to give you a glimpse into this data set here, but I also would cordially invite you, of course, to read the paper and give us some feedback. But what we write in the introduction is that a noteworthy aspect of our dataset, MANTRA, is the conspicuous absence of any intrinsic vertex or edge features, such as coordinates or signals. So in a way, as a side note, this means that the dataset is really purely combinatorial. It is about triangulations of manifolds, but not coordinate-based ones. Because we argue, now returning to the quote, we argue that this absence renders tasks more topological, as models can only rely on topology instead of non-topological information contained in features. Moreover, as manifold triangulations are directly related to the topological structure of the underlying manifold, we study to which extent higher order models are invariant to triangulation transformations that preserve the topological structure of the associated manifold. And to give you a rough idea of the intuition behind that, these are all examples of a similar triangulation of the same object, but with potentially useful coordinates applied to it. And you can see that even though they triangulate the same object, it's really hard to see that it's supposed to be the same object. So geometrically, it's really hard to figure that out. Topologically, it should be easy to do so. And this is exactly the goal of this dataset. We want to force a neural network to focus only on topology and not on geometrical aspects and not on aspects that are in the feature vectors. Now, there is some results, but this is the only results slide that I want to briefly show to you before we then start. The upshot is that if you look at these values, we have a model family G for graphs and a model family T for topological methods. And this is showing the best accuracy or AU-ROC depending on these tasks. And what we see here is that the topological models show only slight improvements over much simpler graph-based models. So even in cases like detecting Betty 2, right? These sort of things we get like from 0.50 to 0.51 or from 0.12 to 0.13. But this comes at the expense of much more parameters and much higher training times. Where they work a little bit better is in the detection of the homeomorphism type. So here we can see that some of them play to their strengths, but we are clearly not quite there yet when it comes to the AU-ROC values or to the accuracy values even. And this I think is a big lesson, because I think it shows that we direly need additional inductive biases to actually leverage the topology of the data. And this brings me to the end. I want to say that I'm really grateful for having this opportunity to talk to you today about what I consider to be a really exciting nascent field, namely topological deep learning. I think it needs much more inputs from other disciplines, maybe math, maybe physics, maybe computer science, to really turn it into like something bigger. I also want to point out that I hope I could convince you that using some geometrical topological concepts actually provides a novel perspective for many machine learning applications. But at the same time, I also want to make clear that this use of geometry and topology needs to be justified and carefully assessed, because otherwise you end up like some of these higher order message passing methods, which are incapable of leveraging very relevant underlying features. Now, still believe the best time to join not only machine learning, but also topological deep learning, the best time to join the field is now. So I would hope that this serves as a little bit of an inspiration to you. And if you're interested in our research and in our research group, then please do check out the website of the IDOS lab. It has just recently been updated magnificently by my group members. So thank you very much for having me, and I look forward to taking some questions now.
Thank you, Bastian. It was a very nice talk. I have some questions, but I will encourage the students to, I think some of them they are already writing questions in the chat, so I will them read their questions to you.
Yeah, thank you, yes.
Kunal, do you have some question? Could you read it out, or do you want me to read it out for you? Okay, let me read out the question since. Kunal is, sorry, it's Kushal. I read his name wrong. Yes, so what Kushal is asking is how to apply TDA techniques on large-scale datasets like large-scale graphs, and what about the scalability?
Yeah, so TDA indeed has a problem with scalability, but there is at least two ways around that. The first is that you just subsample and you apply it to smaller parts. There's some great interesting work by some of my colleagues on distributed topology, meaning that if you just do a lot of subsamples of your space, then you can put together a bigger topological descriptor from those subsamples. That's one direction, although it is of course not clear whether it applies to graphs. But for another direction would be to use another method from the TDA arsenal, namely Euler characteristic transforms. If you have a graph with geometry, with some geometric embedding, then the Euler characteristic transform is really fast. We even have a very nice GPU implementation of it on our website, known as the differentiable Euler characteristic transform. And this really works massively faster than anything I've ever seen in the TDA realm or even the GNN realm for dealing with large scale graphs. But of course, you're right, the scalability issues remain. So TDA as a field, in particular, if it focuses only on persistent homology, has a scalability issue, and we have yet find a way out of that. So except for subsampling and for restricting the dimensionality maybe of the features, there's not a lot of things we can do at the moment, which is why I believe that it's important to understand that TDL, so talking about topological deep learning now, is much more than persistent homology and message passing, right? There's many more different ideas and different notions to be included there, and those can actually then have good scalability.
Thanks, Bastian. Does that answer your question, Kusha? Yeah, he says thanks. I actually has a follow-up question on this. So you mentioned this Euler characteristic transform. Is it only possible for if my graph is embedded in a Euclidean metric space, or is it for any general metric space?
I mean, technically, you could also use it in general metric space. Now, I have to be a little bit careful because I don't want to say something wrong, but I believe it should still work nicely. It's just that you might lose some of the underlying properties that which made up the original definition of the Euler characteristic transform. But in terms of the calculations, I don't think that it's relevant. So for our implementation, we don't check whether it's a proper embedding, right? We just calculate whatever we find, and so we can deal, I think, with general metric spaces and general types of coordinates. But of course, if you want to be strict about it, then you would have to check this first. And maybe this gives me actually the idea. Maybe there is a space for some kind of generalized Euler characteristic transform where you say, well, we do away with this idea of the embedding, and we just say that we assume that we have this data attached to the nodes, and then we work with that.
Thank you. Okay, there is another question.
Oh, I have one question. Okay, just read out the question, and then I will ask. Ma'am, you can read out the question, then I will ask.
So, Shaurav, do you want to read out your question? Okay, I will do it. So Shaurav is first saying, hi, Bastian. Do you know of applications of TDL in 3D object detection from LIDAR point clouds, for example, in Wemo?
Not yet, actually, but it's fun. It's fun that you asked that. That's a very good question, because we have asked ourselves the same question, actually, whether it would not be a good new research direction, because as it happens, we are sitting on lots of LiDAR scans of cities. So if you're interested in this, please do reach out to us. Maybe we can set something up. I would be more than happy to work more with LiDAR data. And to close the loop to what I said earlier, I think LiDAR data is also one of the data sets where we need something like an Euler characteristic transform or something different than your standard TDA persistent homology methods, because that otherwise it will just not scale. But I would be very interested in learning more about this.
Thank you so much.
Yeah, no, thank you.
Argham, go ahead, please.
Yes, so I have one question. So in case of persistent homology calculations, or like higher dimensional Betti number, calculate from the point cloud, just doing by simplicial complex structure, then some filtration technique, after that calculating the Betti numbers. So I have seen there are some methods like Ripsar, and also like Goody, that is Goody software. So i- is there any kind of software that calculate the persistent homologies or Betti numbers of higher dimensional features, like I say 10 dimensional structure, so quite fast? Or
I would say, to my knowledge, Ripser is still the fastest one out there. But even though Ripser has been well crafted by Ulrich Bauer mostly, I think it has its limits as well. So I think it might get you up to 10 dimensions, but it depends very much on how big your point cloud is, unfortunately. So I think to my knowledge, there's no better method than Ripsa out there in terms of current scalability. So if Ripsa can't do it with all the optimizations, of course, right? You should check whether it's the most recent version, and whether all the optimizations that you can get, whether those have been built into the code. But other than that, I think there's nothing that is faster still at the moment.
okay. So Ripsar is the fastest till now.
I think it should be, yeah. But maybe do check out the work by Michael Kerber. So Kerber. He is a collaborator of Ulrich Bauer, the creator of Ripser, and they often have additional papers that show how to speed up the computations even further. For instance, if you have time to do some pre-processing. And I think Goody or maybe some other libraries actually implement these type of pre-processing techniques like a simplicial collapse. Those type of pre-processing steps can sometimes radically reduce the time it takes to do the calculations. But still, I think there's still an upper limit that we are hitting, unfortunately.
Okay, okay. And also another question. So in case of non-Euclidean spaces, non-Euclidean geometry, so can we use that kind like in Euclidean spaces? We use Vettori-series filtrations or other check filtrations like. So
Mhm.
is there any kind of thing in Riemannian like Poincare ball means like non-hyperbolic spaces? Can we have any this kind of filtrations technique?
I think it should still work. You just need to be mindful of the type of dissimilarity measure or distance metric that you're using. But I think it's one of the things that we're not talking about nicely in TDA, namely that often we are not making use of the properties of the distance function. We just assume that we have some kind of dissimilarity function, but it doesn't have to be a proper metric. So if you have if you have something that gives you a dissimilarity between your points, then I think you should be able to at least calculate persistent homology. The big question will be what the interpretation of it should then be. But that I think is up to the application at hand and to the practitioner. But in terms of compute and algorithms, I think it should be possible, in my opinion.
Means you are saying that if we use the Poincare distance metric, the DH that metric, then we can use the same definition for Vettori series. Like if 2 points will be connected, if
Yeah,
that distance will be less than epsilon, that distance for, then we should use that metric. That
yeah,
it will be.
yeah. I
And
think this
for
should work. Yeah.
Ripsar and also Goody, this also works with that.
Yes, this I can actually sign off on. That's true because Ripser has as its input, it supports also distance matrices. So you can just add some kind of general distance matrix in there, or even some kind of general dissimilarity matrix. So again, it doesn't have to satisfy all the axioms of a mathematical metric as long as it gives you a symmetric as long as it gives you a symmetric matrix,
Okay, okay.
more or less.
And another question is in your paper topological autoencoders. So this paper, so you have said that. So I have just read that paper. So you have just you have introduced some loss,
Mhm,
topological loss. So in that you saying that these topological structures will be preserved in the means the latent space.
mhm.
The topological structures will preserve.
Yes.
So, so means why we should use that or that kind of structures? So just to preserve the topological structures, or like you have shown that there is some performances like TSNE plots and also the other plots. They are
Mhm.
not doing that, but your algorithm is with your topological autoencoder structure does that.
Yes.
So what is the means? I am saying that what can be the future means? What can be thought after that means?
Mhm.
Why you have means come out with that result? That I am saying means that
I,
I am not following the question.
yeah, I think what one could do after this is derive better loss terms that actually scale better because our loss term is not scalable very nicely. It only supports 0 and 1-dimensional topological features. But I think nowadays we would know how to do better loss terms, and then we can actually have this as a general loss term for improving unsupervised dimensionality reduction. One thing that I particularly like about this paper is that if you look in the appendix, we even show how to do topology-based PCA. So we show how to use the loss term for PCA. And I think even that shows you that with some minor topology-based modifications, you can actually gain a better understanding of the underlying space. But the hard thing, and this is something where I don't have a proper answer to yet, is how to actually evaluate such representations. Because we have tried to do a very good quantitative and qualitative evaluation, but fundamentally, we often lack the ground truth. We often lack the objective truth of what we would like to have in our dimensionality reduced output. And yeah, as long as we don't have any progress in that direction, we won't be able to actually measure what is relevant. But this might be an interesting direction for the future.
Okay. And also how to come out that means that is the intuition motivation behind that idea. So that
In the interest of time, also you might actually
okay,
take.
okay, okay.
I mean, you can reach out to Bastian. I believe
Yes.
he is open to answer. So there are a few more questions in the chat, which I would read out to you quickly. So Advai is asking, can TDL be a good approach to solving the problem of character segmentation in cursive handwriting? Can pressure dynamic be handled by TDL too?
So for the handwriting recognition, I would say my money would be more on standard computer vision approaches, because I don't necessarily see. I mean, I could be wrong now, right? I'm not discouraging you from trying it out. I'm just saying, like, if I had to design an algorithm from a priori principles for handwriting recognition or for character segmentation, I would probably go with a computer vision algorithm first, so with a convolutional network. At the same time, whenever you have a way to model your data plausibly as a graph or as a simplicial complex, and I'm saying plausibly in the sense that it should be for some specific purpose, right? If you have graphs that you want to take a look at or that you want to classify, for instance, then I think this TDL perspective can be helpful. But I don't think it will necessarily directly outperform techniques from computer vision yet. Sorry.
Thank you.
Thank you so much. There is one more small question. So Dipankar is asking, is there an application of TDA for data quality management?
Oh, that's an interesting question. So I'm not sure whether I know everything about data quality management, but one thing that you can do is you can measure, for instance, how well a compression algorithm retains certain features in the data, if that's what you mean. Or for instance, you can use TDA applications for ways to evaluate different models, for ways to look into differences between different models. So we had, for instance, I think it's now more than 10 years almost or something like this, we had a paper out there for clustering quality assessment using TDA. But yeah, but beyond that, I'm not really sure what other tasks there might be relevant for data quality management.
Thank you so much. I don't see any more questions here. I actually had one question about the Olivier-Ricci curvature. You mentioned there at some point that something is learnable, and I wanted to understand what is the definition of learnable in this domain. So it's not learnability that you were talking about, or is there an analogous definition here?
Yeah, no, so actually it's not learnable yet. So my point was to point a little bit into the future. I wanted to say that currently when you calculate the Olivier-Ricci curvature, one underlying component is this probability measure that you assign to a vertex in the graph. And at the moment, most of the time when I see applications in the field, they use a static definition of this probability measure. So they say, for instance, that the probability measure is defined by the degree of the node and nothing else. But I believe that it would be interesting to have this probability measure as some kind of learnable function that you put on the graph. And so having two vertices, even though they might have the same degree, maybe it would be useful to give the algorithm an opportunity to learn two different type of probability measures for different types of vertices. And I think that might be useful for future applications. But I was also trying to open this up to the audience a little bit. So this is one of the problems that we don't know at the moment how to tackle, or that we're not actively tackling at the moment. So if some of you are interested in this and have some ideas, then please let us know. We would be more than happy to discuss them with you.
Sure. Thank you so much, Bastian.
Thank you very much.
I don't see any more questions. So I guess with that, we will end this session. It's an excellent talk. I learned a lot. I am not really from this field, and you got me interested. I guess the students also got interested about the topological deep learning and more about to do more with the topological structures. So thank you.
Thank you very much. I'm glad to hear that. And thank you for this wonderful opportunity. I'll update the slides because I saw 2 or 3 mistakes on them. This is, and I will send them around to the organizers, and then please feel free to distribute them. And yeah, of course, contact us if you're interested in any of these.
Sort of about the LIDA data, is I think very willing to reach out to you.
Yes, yeah, of course, yeah, no, more than happy to get talking about this.
Thank you, everyone. Although we
Yes, yes. So thank you, Professor Bastian, and also Dr. Sanjukta for addressing the questions, and also these are very excellent talk, sir. Thank you. I think we should invite you once again in the next year also.
Thank you very much. I would love to come. And yeah, if
Yes,
any
sir.
of you have questions, just let me know. And so yeah, I would say have a great afternoon, everyone, and hope to hear from you soon. And have a great time, all of you.
have
Yes,
a
sir.
good weekend.
Thank you, you too. Bye bye.
Yes. Thank you. Thank you, everyone.